deviation function. So this will be essentially, everything will be microscopic today. I really care about the occupation of each site, and I will try at the end to extract the large deviation function of the density. And on first day, with a totally different approach, which was developed by a group in Rome, Bertini, De Sole, Gabrielli, Jonalasigno, and Landim. They could get the same answer by a purely macroscopic approach, which their approach is in principle valid for much more general systems, but it reduces. Okay, you have to solve equations that I have to write, and usually it's difficult to write to solve these equations. Usually there is no solution. Okay, so let me start with exclusion processes. So yesterday I talked about the simple symmetric or symmetric simple exclusion process. You remember you have, this is a one-dimensional version. There is, you can look at the problem in higher dimension. So here you have a rate alpha and gamma at which particles enter. Here it's beta and delta. Okay, and you remember particles can only jump at rate 1 to one of the neighboring sites, and with the same rate on both sides. Okay, now there are several versions. The asymmetric exclusion process, which is just the following, that the particles, so the rates at the boundary can be the same, but a particle can hop to the right with rate 1 and hop to the left if the site is empty with rate r. So essentially, the particles tend to move, if r is less than 1, they tend to move to the right. Now, there is, for the theory, there is one version which is important, which is the weakly asymmetric, where just r is exponential minus say lambda or q over L or something. Okay, lambda over L. So this means that the asymmetry is weak, and essentially the theory that the group in Rome developed applies to this and that, but not this one. This one corresponds to what's called the KPZ equation, and I am not sure I am going to discuss that too much unless I have time for the last lecture. Now, one case which somehow is simpler is the case r equals 0, where they just cannot be, they cannot jump to the left, and this is called the TASEP, totally asymmetric process. Okay, so this is the models I am going to discuss, and now I would like to see what I can compute. So I want to compute, so I am interested in the steady state, but I can try to compute the evolution of the occupation number. So I have a variable to I, which is 1, which means that it's occupied on each side. So I is from 1 to L, and 0 if it's empty. Okay, and in order to write the evolution, so I am going to write the evolution in the two cases, in the case of the SEP and in the case of the TSEP. But you can write it in all cases if you like. So in order to write the evolution, I want to think of a time t plus delta t. So I want to go from time t to time t plus delta t. So in order to know what happens at time t plus delta t, I want to say, let's first average on what happens in the very last part, and then I will average over the whole process. So let me call, when I will do an average, I call it like this, and when I want to average over what happens at the very last moment, I do these double brackets. Okay, so let's imagine I want first to average over this. So this means that I know the configuration at time t, and I want to know what is tau I at time t plus delta t. Okay, so but tau I is known at time t, so there is no fluctuation. So tau I at time t plus delta t is probably either 1 or 0. And how is it possible that it is 1? Okay, it is 1 if at time t, so on this side I write properties at time t, so I'm not going to write tau of t. So at time t it was occupied and the particle did not leave. Okay, here I am talking about the set, maybe I should say first. So it was occupied and the particle did not jump to one of its neighbors. So it was 1 minus delta t times 1 minus ni plus, sorry, 2i plus 1 minus delta t 1 minus 2i minus 1. So ever it was already occupied and the particle, a particle did not escape because it could escape with probability delta t if the site on the right was empty and the same on the left. Or there is a possibility that it was empty. So it was 1 minus 2i, and then the particle moved into that site. So this would be delta t times 1 minus 2i plus delta t. Oh, okay, so I don't need here. Sorry. This will be 2i plus 1. So there was a particle inside I plus 1, or delta t 2i minus 1. Okay. And 0 is just 1 minus all this probability. This would be, because it can only be 0 or 1. Okay, so let me see what the evolution is. If I just average over the very last time interval, so tau I at time t plus delta t, okay, I have just to sum this, and so it gives me, okay, it gives me, in fact, the 1 gives me tau I. Sorry, here, at the moment, I have not done any average, tau I, and then I get plus delta t. Okay, there are some cancellation of the nonlinear terms. If you look at it, you see tau I plus 1, they go. Okay, so there is a plus here. And I get delta t plus tau I plus 1 plus tau I minus 1 minus 2 tau I. Okay, so again, this is an average over the very last time interval. And now I can take the full average over the whole time interval. And then I get, and I get that here I can have average here and equals average of this whole thing. And then I get d tau I over dt is just tau I plus 1 plus tau I minus 1 minus 2 tau I. Okay, so that is not a very complicated thing. So there is two things to remark. That's for the SEP. First, you see that it's a diffusion equation. So it's a diffusive system. The other thing is that although particles interact, this is a closed equation. That is, when you want to compute the evolution of tau I, you don't need to care about higher coefficients. Closed, so you just need to care about the average occupation number. You don't need to care about correlations. Now, if you are interested in the current in the system, then what is the current is, so it's, I take two sides I and I plus 1, and it is how much flow I have through this side. So the current between I and I plus 1 is, the average current is 2I 1 minus 2I plus 1. So this is the flow from I to I plus 1 minus 2I plus 1 minus 1 minus 2I. So the current between site I and I plus 1 is just 2I minus 2I plus 1. Okay, so this is easy. Okay, so this is what you see for the SEP. Now, the same calculation you can try to do for the TASEP, and we will see that. So I'm not going to redo it. You can think of it as an exercise. TASEP, then you would find that d to I over dt is equal to, TASEP is just, they can jump from only to the right. To I, 1 minus, sorry, it's, okay, let me see what it is. To I minus 1, sorry, it's 2I minus 1, 1 minus 2I, minus 2I, 1 minus 2I plus 1. So, okay, to say it quickly, how the occupation can increase on site I. Maybe site I was empty and a particle jumps from I minus 1, or it was occupied and the particle left to go to I plus 1. And you see here, the problem is, a priori, it looks more difficult because now you see it's no longer closed. If you want to compute tau I, you see you need the average of tau I minus 1, but also you need this two-point function. And this is typical of what people call the n-body problem. That is, if I could write an equation for the evolution of this two-point function, but it would involve three-point pairs of points at larger distances and so on. So essentially, I need to compute all the correlations if I just want to know the average. Okay, so this is somewhat more difficult. So we will come back on it later today, but just to make you feel that the problem is more difficult, at least from this point of view. Okay, now, so let me now come back to the SEP and see what I can compute. It's a diffusive equation, and so in the steady state of the SEP, steady state profile of the SEP. Okay, so steady state, you see I have already the equation here, and in the steady state, this means that d to I over dt is 0. Okay, the system reaches the steady state. Now, what I wrote here is the evolution in the bulk, but I could write, you remember, I don't know whether it's still drawn here, I have rates beta, delta on the last side, and alpha, gamma on the left, and the beta, delta on the right. I could write the evolution, which is slightly modified on site 1, because I have to take into account the rates, these rates. And so, for example, I write it on site 1, and you have something similar on site L, d to I over dt is alpha 1 minus 2 1 plus 2 2 plus 2 2 1 minus 2 1 minus gamma 2 1 minus 2 1 1 minus 2 2. Okay, so okay, here I just need to average over everything. So how can I understand? You see, I can write it directly because, okay, at which, how to one, sorry, this is site one, how to one can increase. Okay, it was empty and a particle entered, this is the first term, or it was empty and a particle came from side two, this is the second term, or it was occupied and the particle left with rate gamma, so this made tau 1 decrease, or it was occupied and side 2 was empty and it could move there. So this is an evolution, and so in the steady state I have this equals 0. That's steady state. And so I have a system of equations, of linear equations, and I have something special on the first side, I have something special on the last side. I can solve the problem and I get, okay, I write the answer. This is just a linear problem. You see, already, if you are in the steady state like this, you know that tau I can at most be linear in I. It cannot be anything else. So you can solve it and you get that tau I, okay, let me write the formula, rho A L minus plus, okay, I write it B plus rho B times I plus A minus 1 divided by L plus A plus B plus 1. And I have to tell you what all these things are. A is 1 over alpha plus gamma. B is 1 over beta plus delta. And rho A is alpha over alpha plus gamma. And rho B is delta over alpha plus, beta plus delta. Okay, so this is one way to write it. And you see, of course, it is linear in the position of the site, and you have an explicit formula. And there are two things one can remark. Okay, one thing already you can remark is that let's imagine that some of these numbers are very small. Alpha and gamma are very small. And what it means, if they were zero, this means that there would be no contact with the reservoirs. But if they are very small, this means that this parameter A is very large. Now, if A is very large, okay, essentially the system is in density rho B. It's because when A is very large, only this term survives. So essentially, the system is just the density is just that of rho B, and the same on the other side. So this already shows you that the strength of the contact is important in this problem. Here, this one? Okay. Alpha, okay, it would be the same. Okay, but I have taken I could say alpha times this plus the average of the rest. So this is your question? I'm not sure. Oh, sorry. Yeah, yes, I'm sorry. Yes. Okay. Now, already, the other thing I want to mention, imagine that the contacts are not very weak. So this means A and B are of order 1. And now I think of a very large system. So I would get that if I call I equal so Lx, so x will be between 0 and 1. Okay, this, if B and A are of order 1, for large L, I get that rho, the tau I, which I want to call rho of x, will be rho A 1 minus x plus rho B times x. So I get a linear profile, and I get also that the current is tau I minus tau I plus 1, okay, because, okay, maybe I discuss it, it's already here. Okay, the current, of course, in the steady state, you find that the current doesn't, if I take tau I minus 1, the current does not depend on I, which it should be so, because the system is in the steady state. So if current the average current at site I was different from site I plus 1, then particles would accumulate. And you find that the current is rho A minus rho B over L, and this dependence, the current decreases with the system size, is called Fick's law. And it's very much like, I don't know, at school we learned first Ohm's law. You know, the resistor is proportional to the length of the, okay, to its length. So this is very similar. Okay, so this is Fick's law. Okay, so that's all things which are simple. Now let me come to discuss the two-point correlations, because this will be, okay, steady state correlations. If you have questions, please do not hesitate. Okay, so I can write very much as I did. I just write it directly, the evolution of the correlation between two sides. But in fact, because of the exclusion, I need to worry about whether I take two sides which are neighbors or not. So let's first write J larger than I plus 1. So they are not neighbors. Okay, you can write it and you get 2I plus 1, 2J plus 2I minus 1, 2J plus 2I, 2J plus 1 plus 2I, 2J minus 1 minus 4, 2J. 2I, 2J. Okay, so essentially when they are not neighbors, each particle is diffusing. That's what it says. But when they are neighbors, you have to be a little more careful, and you get d to I plus 1 over dt equals 2I plus 2 plus 2I minus 1 2I plus 1 minus 2I plus 1. Okay, so whatever it is. So here are the evolution equation. You are interested in the steady state, so you write that all this is 0. And then if you make the effort, you also write what happens if one I is at the boundary, j is at the boundary, and so on. So you have a few more equations to write if you like. There is no point that I write them. The way to write them is very much what I have shown, but I want to tell you what the answer is. And the answer is the following. So I write the full answer first. You get, okay, okay, let me write it. So you can think of it as being an exercise, and it's maybe, okay, for what I'm going to say next, instead of computing only the correlation function, I want to remove this product here. So in fact, this is really the correlation. And these terms we already have, so you do that, and you get this is the following: minus rho A minus rho B squared times I plus A minus 1. Okay, this is L plus B minus J, and divided by L plus A plus B minus 1 squared L plus A plus B minus 2. Okay, whatever these precise expressions are, but there is absolutely no difficulty to solve these equations, and this was already obtained about more than 40 years ago by Spohn. I think it's in 84. Okay, but the thing there is something rather interesting in it, is that if I look at the system on large scale, that is, I say I is equal to Lx and J equals to Ly, and this formula is valid for I less than J, then this becomes minus x, 1 minus y, rho A minus rho B squared, divided by L. Okay, so the correlations, let me write the correlation of the density rho x, rho y, and there is a minus sign, and this is given by that. And this, you see, this is a straightforward calculation, but that I have just told you how to get to do it. But what is very important is that, you see, as soon as the system is out of equilibrium, that is rho A is different from rho B, you have correlations. You see, if there is no, if the densities are the same, the system would be at equilibrium, then there is no correlation, but there is this correlation. And one thing you could say, okay, these correlations, after all, if the system is very large, we don't care. So you could think that these correlations do not matter. But the answer is they do matter, and in many respects. So the first way to see that they matter is, let me try to consider the number of particles in the system. So these are steady state correlations, and the number of particles in the system is just sum over tau I. Okay, so tau I know what it is. For a large system, n will be L times rho A minus rho B over 2. Okay, so that's... Now, if I am interested just in the fluctuation of the number of particles, okay, so this would be sum over I, sum over J of tau I, tau J. Okay, minus tau I, tau J. This would be, this is just the variance of the thing. Now, just to say it with words, okay, here the correlations between sides which are not the same is of order 1 over L. But here there is a double sum. So this means that the contribution of this will be of order L. So in other words, these long-range correlations, although they are very small, if I am just interested in the fluctuation of the number of particles, then they will matter. And so if you do the calculation with what I showed here, okay, there is, in this term, there is the term sum over I, tau I squared, but tau I squared is the same as tau I, minus tau I, because there is a diagonal term, plus sum I less than J of tau I, tau J, minus tau I, minus tau I, tau J. Okay, so this term is of order L, and this one also. And if you do the computation, you get that, okay, whatever here there is a term, but this contribution here is L over 12 rho A minus rho B squared. But what is important to realize, even if you look at these fluctuations, already this dependence here matters. Okay. Yes, please. Sorry? Sorry, N is this. I'm sorry. Yes. Yes. Okay. N is defined this way. Now, N average would be this. And yes. Now, what we learn also, what we are going to learn also from that is the following. Is that already just with this calculation, you will see that the large deviation function of the density is non-local. Sorry? Sorry, this is the average of n for large L is given by that. Rho A minus rho B over 2. Sorry, it's rho A. Yes, I'm totally sorry. It's plus, yes, plus. Yes, I'm sorry. Yes, I'm sorry. Thank you. Okay, sorry. Okay, so now what I want to show is that the large deviation function of the density is non-local. And okay, hopefully by the end, we will find a way to really tell what it is, but at this stage, I just want to convince you that it's non-locality of the large deviation function. Non-locality of the large deviation functions. Okay, so what is my strategy? That instead of looking at truly the large deviation function, I want to compute its Legendre transform. So I am interested in the steady state by this quantity, sum of lambda I to I. And you see this quantity from I equal 1 to L, okay, is sensitive to all the correlations in the system. And okay, this quantity, in principle, in fact, for the SEP, one has a closed expression for that, but I am not going to write it at all. But let me just do the following. I want to take the log of that, and I want to consider that lambda, all the lambda i's are small. So I just need to expand this exponential and to take the log. And so what I get is the following. If I take the log, I get sum over I of lambda I to I. All the lambdas are small, plus sum over I lambda I to I squared, sorry, lambda I squared to I squared or 2I is the same because 2I is a variable which takes only value 0 or 1. And then I have plus, I think there is a 2 here, okay, sum over I less than j of lambda j to I to j. Okay, and because you expand the exponential and you take the log, here you get the truncated correlation function. Okay, so this is just algebra, and then plus order of lambda cube. Okay, so this is just an expansion of the exponential. Okay, it's a parameter. It's just okay. You call it, you can call it whatever. But I am just interested in the situation where they are small. Now I might be interested also when they are not small, but at the moment I just look at that. In fact, there is a closed expression, but it's technically it's more difficult to obtain for all values of lambda. But here, just to convince you that the thing is non-local. Okay, fine. So this is what it is. And now let me imagine that the system is very large and I am interested in what happens in large scale. So I say, let me take lambda I equals lambda of I over L. So this, this will allow me to look at what happens to the system on very large scale. So let me make L very large and look at what happens on very large scale. Then all these sums, because, okay, here I think I made also a mistake. Okay, but this part does not interest me because it will not contain any long-range part. But anyway, if you make this lambda very slowly, then what do you get? The first term will be sum. The sum here will become an integral. So the first term will become L integral of lambda of x, the density around the point x, plus L over 2, the integral of lambda squared of x times rho of x, 1 minus rho of x. So these are the two first terms, which are local. But the long-range correlations, which are there, they tell me that plus, so there is a double sum, so I will get a lambda L squared, and so there is a 1 over L here, so it will be L times, okay, there is a 2, if you like, integral from 0 to 1 dx, integral from x to 1 dy, and then this thing, rho of x, okay, in this problem, it's 1 minus x, 1 minus y, times rho a minus rho b squared, times lambda of x, lambda of y. So already this generating function is already non-local. You see, it points at position x and y, which are far away, which are at distances of order L. They just contribute. And okay, and you could continue the story and go to higher correlations, but already at this level, you see that this Legendre transform of the probability or this generating function is non-local. And so if you try to invert to get the probability of any density profile, it won't be local. So this is rather easy calculation to do. Okay, so this, unless you have questions, I know I am going to move to. Yes, so if you make it a delta function, you will, yes, okay, you can do whatever you like. But if I, you see, in principle, if I want to know what is the large deviation function of the density profile, so you remember I would say the probability of observing a certain density profile in my system would be exponential minus L f of rho of x. Okay, so I am looking at the system on large scale and I see a certain density profile. If this is local, okay, the relation between this quantity here, G, okay, let me call this Lj, G will be the maximum over rho of x of lambda of x, integral of lambda of x, rho of x, minus, this is just a Legendre transform. So you see that if F is local, then G will be local. Okay? And if G is not local, then F is not local. But anyway, we will come to that. So if you have no questions, now I am going to move to something else.
There is a question.
Yes.
Now, all this analytic discuss comes actually from a particular power correlations, right? So it's one
Yes, yes.
it will be bigger or smaller, and it's all very different story, right?
Yes, but for all diffusive system, it is like 1 over L. So you see, this is particular model I am discussing, but tomorrow and the day after, I will look at the system on large scale. I will look at the macroscopic theory, where the really important thing is fixed law in this theory. So we'll come to that tomorrow.
Is it also a fixed law? Because now it's not about like the current, but about the point function. It's also kind of scaling position.
It comes from the fixed law. Now, for some particular models, we will see tomorrow how to compute this from a macroscopic point of view, and we will see where fixed law enter, and also what are special cases where you have not this correlation.
But so then, so if this power will be like, for example, L squared, so this term will just disappear. Well, this will be dominating.
Yes.
I think there will be like, for example, a square root of L. So what is that? So then this term is even like dominating.
Yes. Okay. Okay. If okay, so imagine that it is 1 over square root L, would be in big trouble for the following reason, because something like L to the 3 halves.
And then to the next term is even bigger.
Okay, this would, but this object here, the density, okay, sorry, the quantity I defined here, exponential sum over I of lambda I to I, it cannot be larger than exponential L. It cannot be L to the 3 half, because this is of order 1 and this also is of order 1. So, okay, but if this would happen, this means that the thing is non-analytic in this lambda or things like that. So okay, but for diffusive system, here I talk about diffusive system, it's always 1 over L. But we can discuss it more if you like. Okay, so now, before the break, okay, so the last 3 minutes, I just want to say now, for all these models I talked about today, all these exclusion processes, it turns out that one can get an explicit expression of P of so the stationary, P of to1 to L. One has an explicit expression in terms of product of matrices, which I am going to explain. So essentially, the way it is that the stationary state will be of the form a left vector, a product of matrices xi to L. These are matrices times a right vector, and these matrices have two possible values. D if the site is occupied, and E if it is empty. So this kind of things, they have been used in quantum chains to get the ground state of quantum chains, for example. Okay, so this is what I am going to show is that the steady state can be written like that for all these exclusion processes. And then we will see what we can extract from that. And if I have time, I will get to the full large deviation function of the density in the case of the set. But the goal is first to say, okay, how should you choose these matrices and vectors in order to get the steady state? So you see, this represents 2 to the n numbers, because for each xi I can take two possible values, and here I have 2 to the L weights. Okay, so maybe we stop here and then we'll continue with that. Ça va à peu près ou ça? Bon, il faut m'arrêter hein, parce que je ne me rends pas compte que des fois on dérape un peu. Okay.
I mean, so the whole idea with the like generating functional in the approximation, like I mean, it's essentially like we're solving like we have an equation for different p with like different charge sectors based on like previous lecture. We do essentially a Laplace transformation as we like where we solve differential like equation for like in time, right? So like we do I understand correctly that what we do when we introduce some of our like equals that is effectively we want to like after that to calculate something that depends on who we would do something we would do something like that.
Yes, if you like. Yes.
Okay, yeah, okay, and it's yeah, and then
Okay, you have to invert the Laplace transform. Yes.
and so and that's yeah, and then we're going to get the saddle point for like area. Then the expansion of like the saddle point expansion of that integral.
Yes, yes, if you like. Yes. If you want to, okay, I would do it in a different way, but that's the way to do it.
Okay, thank you. Just to make sure. I have a question, or maybe you will explain this after the break. All of this. But what are those? Because it looks very similar, like this construction with a product of matrices.
Yes, that's
Like
exactly.
a matrix product state with a certain configuration and a left and a right, like
Yes.
it's like steady. What is it? Fixed point.
Yeah,
Is
yes.
that what it's?
Yes, okay. Here it will give an exact thing. Now people in the MRG they use it as approximations, but some models can be solved exactly like that. So these models can be solved exactly this way.
I was wondering
Yes.
if you look at the higher moments,
Of what?
like the fourth moment or something, it will probably also scale with L.
Yes, 1 over L cubed for the 3-point correlations, 1 over L. Yes, but because you see when you okay, I've erased that. But when you write, if you write sum over I lambda I to I, and you expand it in powers, so the first thing will be lambda I to I, okay, which will be of order L. The second thing will be I to J minus. Okay, so this is 1 over L, this is, but there are L squared. The third thing will be some I, J, K. You can, anyway, with this matrix product, you can compute everything you like.
Oh, okay, okay.
Well,
Because I was wondering, because here you took L small, and then you use that expansion on that board,
yeah,
you discretized I,
yeah, yeah.
no longer small.
I,
Like at a certain point, you said, okay, now we will take Li to be big I over L,
yes,
and let I run from.
yes. I don't say that I is small. I say that in this expansion, lambda I is small, but
But then you use that expansion.
I use this expansion just to illustrate the fact that it's non-local. Okay, but we will see that it's non-local by other means.
Just for illustrative purposes.
Yes.
It's not like you use, like that was the final thing.
No, it was just to give you the feeling that already without, okay, this is a limited effort. That is just that you already say that it's non-local.
Sorry. Excuse me. Can I ask you a question about that? macroscopic fluctuation theory.
Yes,
Why
but
doesn't it work for, say, ASEP? So I know that Skype is either.
because okay, I because essentially you see this macroscopic is true for diffusive system. The ASEP is not diffusive.
But you can use macroscopic fluctuation theory for, say, subdiffusive system. It works. I don't see a reason why not. I mean, in the end, you write down. I mean, I may be naive. This is what you're saying. You write down an action, and the certain point of like on-share relation is given by the Kaiser PD. Then fluctuations or corrections around this set point are PD corrections. So for example, for dipole conserving system, it's possible to write down some sort of MFT.
Okay, maybe okay. I think that okay. One thing is some people look at long range problems and so on, but you see the fluctuating hydrodynamics for driven system like ASEP is like Kripke equation. It's not like diffusive equation. So and it changes the exponents, it changes the long range correlations. I will mention that, but I am not sure how to answer your question because I would need to look you would need to tell me more precisely what problems you have in mind, which are not diffusive.
Yeah, I mean, for example, I don't know. I mean, I'm working in anomalous transport and also in large deviations, and
Yes, so for this anomalous transport, for example, the correlations, they would not be like this. So
yeah,
I don't. There would be some power laws there.
it's different scaling that this dynamical exponent is whatever we can hook up. So
Yes.
it's not that.
Yes, you see, in all these things, I can, when I considered these quantities here, everything can be expanded in for diffusive system in powers of lambda and so on. If you do it with systems where the correlations do not scale like 1 over L, it will be singular. You get things which you cannot understand by perturbation theory. That's my understanding.
If I remember correctly, for example, in ballistic systems, it has been developed with this GHG perspective, this generalized hydrodynamics perspective.
Okay.
You can still write down like a well-defined scaling cumulant generating function, and then the limit exists. You can calculate down cumulants, and I mean,
Okay.
there are subtleties because you have a linear degenerate system, and it's integrable, so it has a bit of problems, let's say. You still can do it. It's just I don't know. When I
Okay, so maybe you say tomorrow and the day after, I will talk more about this macroscopic fluctuation theory. So maybe after that we can talk more if you like. But okay, I'm sorry.
yeah, thank you. I'm just yeah.
Okay. Okay, so so what I say is that for the so you see all the exclusion processes I discussed are just particular cases of the ASEP where particles can hope with rate 1 and on the left with rate R, and there is still this exclusion property. Now, when I okay, when I say that, okay, let me just say what it means to say that the weight is given by this product. So imagine I have a configuration, and I would like to know what is the probability of this configuration. So I have 3 occupied sites and 4 empty sites. Then the probability of this configuration, see here, will be d cube E4 W V, and these are the weights up to a normalization. Now, what should I put in the denominator? I should put the sum of the weights of all the possible configurations. So the normalization will be W, okay, D plus E to the 7 times V. Okay, so this is the probability of seeing this configuration up there, because 3 sides, 4 empty, and here I have the normalization, because here I have to sum the weights of all possible configurations. So if I sum over the occupation, the possible, whether the first site is empty or occupied, I have D plus E, and the same for everybody. Okay, so this will be the weight of a configuration. Sorry? D are matrices. So I will tell what these matrices, what to do with these matrices. I will try to explain why this is a steady state. And more interesting is, what do you do with that? What can you compute? What do you see? Okay, so for all these ASEP, so I write it for the ASEP, and then I will concentrate more on some of the models, but you can do everything for all the possible models, but the calculations, I want to not to go to things which are too complicated. So the story is that the matrices D and E satisfy the following algebra. R E minus D equals D plus E. Okay. And that the vectors W satisfy alpha E minus gamma D equals W. And so I will try to show you why it's so. Beta D minus gamma minus delta E V is equal to V. Okay, so the claim, and I'll try to convince you that this is true, is that if you are able to find matrices and vectors which satisfy that, then you have the steady state of this problem. Now, let me just tell you why this simplifies life. You see, in principle, if you want to look at the steady state of a system of size L, you have 2 to the L weights to compute because there are 2 to the L configurations. Now, in fact, here, because of this, I have only of order, say, L squared. So I have L squared numbers to determine. Why is it so? You see, if I have an arbitrary configurations, it would be D something N1, E M1, D N2, E M2, and so on. And because of this rule, whatever word I have, I can always, by each time I have a D in front of a E, I can switch them.
What's the factor in front of ED over there? What is it?
R is just,
As a star.
it's this rate here. Okay. So whatever, whenever I have a D in front of a E, I can switch them. So essentially, if I have a way to compute all the words of the form EMDN, that's it. I will be able to compute everything just because of this commutation rule. Okay, so this makes life easy. And these numbers might be rather simple. Let me just take an example. Which would be the TSEP with, okay, remember alpha here, gamma there. This is just an example, but you can do it for everything when gamma and delta are 0. Okay, so when gamma and delta are 0, you see that all the d's on the right, this number in this case is just 1 over alpha to the n, 1 over beta to the m. So for this special case. But otherwise, you might have to compute a little more. But so you know the weight of all these configurations, and because of the commutation rules, you can do it. Okay, so now what I want to show you is why this solves the problem. And to do that, okay, you can, I want to, okay, I'm going to do a calculation by showing you what happens for one particular configuration, but when you understand how it works for one configuration, you will understand for all of them. So let me just take, let me just take this configuration that which was somewhere here. Okay, so I take this configuration, it has 7 sites. All these sites are occupied, and all these sites are empty. And so the weight of this configuration is W D3. There are 3 Ds, E4, V. Okay? And now, okay, now particle might leave here, particle might move, a new particle can enter. So essentially, from this configuration, there are a number of over configuration which can be reached, and I am going to draw all of them. So okay, so this, for example, I could reach this configuration with a particle which enters. So I have a rate alpha to go from here. And from here, I could go there at a rate gamma, because this particle might move outside. Okay, so this is the rates. Now, I could also, you see, I have taken one particular configuration to avoid too complicated things. So now I could go from here to there if there is a jump. So I go there with rate 1. And this I can go with rate r because the particle moves to the left. And the last thing is And it could be that a particle enters here with a rate delta, and this is beta. So these are for these particular configurations. You see, if I had more clusters, I would have more lines here. Okay? So, yes? Because, okay, I said that the weight is x1, xl, and x is a matrix, and x1 is D if the site is occupied, and E if it is empty. So here I have a D, then I have another D, then I have another D, and after that it's empty, 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 for this specific one. Okay. So now, let me see what happens. Okay, so now the weight of this one, there is the weight of this one. So there is, when I am in this configuration, I can escape from this configuration. So this means I am going to lose the weight of this configuration. So what do I lose? And what do I gain? So sometimes I am in this configuration and I move away, and sometimes I am in another configuration and enter there. So what is the how much I lose here? Here I yes. So when I am here, I might go there. So the loss is W d cube E4 V. And the gain is, what is it? It's alpha times W E d squared E4. Because I gain from here, you see the weight here is E d squared E4. Okay? And let me do it for the second line. I get here, what is the loss is W, there is a rate 1, d cube E4 minus V, and the gain is R times W d squared E d E3 V. Okay? And the last thing, you do it again. What is the loss? It's, okay, it's delta times W d cube E4. And the gain is W d cube E3 d V. And there is a beta. And in order to show that in order to show that it's a steady state, I need that these two quantities are the same. The sum of these two quantities are the same. Okay, so let's see what the first line gives me. You see, I see that I have gamma d minus alpha e. Everything is the same, except I have alpha e minus, so let me look at gain minus loss, minus what is lost, and it's, so I have alpha e minus gamma d, but alpha e minus gamma d, I know what it is. So the first line gives me W d squared E4. Because you see, I am using alpha e minus gamma d, and alpha e minus gamma d, I know that it's just 1. So okay. Now, this term here, okay, gain minus loss, I get, at the boundary, I have a dE minus R ED, which I can read over there. And then this tells me that the sum of, okay, so there is a minus, and I have W times d squared times d plus e times e3. Yes. And if you go to the last thing, you use the last formula, and then you get plus w. Okay, so you have d cubed e3. Okay, so you see, you make this difference. Okay, I hope I do it right in the blackboard, but I can tell you that it works. So you do it, and whenever you see beta d minus delta e, you look at what's there, and then it simplifies. And at the end, you get a kind of telescopic sum, and you see that this is 0, because okay, you just do the computation, and this is 0. So you have d squared e4 here, which simplifies, and d cube e cube, which simplifies. Now, if instead of looking at this configuration, I had put more clusters, then the simplification would be the same, except you would have more lines. But that would be okay. So, okay. Okay, so now I'm go. Yes, okay, now I come to that. So do I need to tell what the matrices are? No, it could be that there are no matrix which works. But from what I said before, you see, I told you that you can always reduce all words to simple words where all the e's are on the left and the d's on the right. And essentially, you don't need to build these matrices. But in a number of cases, it is useful to do it. Okay, now, and I will use that in a minute. Okay, so now I want to work with that. So let's accept that these weights, where the matrices can take these two possible values, give the steady state. I just give you the reasoning in a simple case, but it's true for all configurations. Now, what do I get from that? Yes. In principle, you could do that, but then you would have to write 2 to the L lines, which is a problem. But in fact, the way of reasoning is that the only thing which matters are the clusters. So you realize that each time you have a boundary between occupied and empty, then you have relation, you can use this relation, and then there is always a telescopic sum. So it doesn't matter the number of clusters you have. But okay, you can do it, but I don't want to enter into more complicated calculation, but it's not very complicated. You see, this example is really generic, what I have shown here. Okay, so let's see what you can compute with that. The steady state properties. Okay, so I want, for example, in the steady state to compute tau I. Okay. So this means that I want the site I to be occupied. So I have a D at position I. And I don't care about what happens for all the other sites. So all the sites before I don't care what they are. All the sites after, I don't care. So this would be the formula. And in the denominator, I have a normalization factor. So if I have these matrices in my hand, then I can compute the occupation number. If I want the correlation function that we discussed earlier, to J equals W D plus E to the I, D plus E, then there is a D here, D plus E to the J minus I minus 1, D, D plus E to the I, L minus J, V, and then I have the normalization. Okay, so I can compute essentially all correlation function. Okay. If I am interested in the current, between site I and I plus 1, okay, so it is just 2I, 1 minus 2I plus 1, minus R, 2I plus 1, 1 minus 2I. Yes, because between site I and I plus 1, a particle moved from I to I plus 1. So the formula would be W, then I have D to the I minus 1, dE minus R ED times D plus E to the L minus I plus 1 over V. Okay, so I can compute the current. I have, sorry? Yes, absolutely. Yes. Okay, I'm happy that follow. Okay, so this is, and because of the third line here, it is just the current will be W. I can simplify this. It will be D plus E to the L minus 1 V times. So if I am interested in the current, I just need to know this normalization. That's it, because dE minus is just D plus E. Okay, so I can compute something. I can compute correlations. Now, you see, you remember maybe when we computed the correlations for the SEP, we found that the correlation was linear in I and was linear in J. Okay, so when it's linear, this means that if I make the difference between I and I plus 1, it does not depend on I. A function which is linear in I make the difference between I and I plus 1. Now imagine that I try to change this I by 1. I want to go from I to I plus 1. Then the difference will be dE minus ED. dE minus ED for the SEP is D plus E, so it does not depend on I. So you can get immediately that for the SEP, all the correlation functions will be linear of each coordinate this way. Okay. So yes, okay, so now we come to that. Okay. Now for the rest of this lecture, I am going to take two examples. There are many things you can compute with that, but I am going to take two examples. And the first example will be on the TASEP, and you will get the phase diagram of the TASEP. So And for the phase diagram of the TSEP, okay. So you see, as I said, you don't really need to know what to build these matrices, and maybe there might be many representations of the matrices which give the same answer. But sometimes it's very convenient to have one specific because you can do the calculation in an easy way. So this is what I am going to do now. I think it's 8 or maybe 7. It's phase diagram of the TSEP. So the TSEP, you remember, and I want to consider the situation where alpha here, beta, and there is no gamma and no delta, so gamma and delta are 0. So particles enter on the left, leave on the right, and they can only, the TSEP, they can only jump to the right. They cannot come back. Okay, now, you see, you can do for general and so on, but let me show you a matrix form which solves this equation. And the matrix is just the vector is equal to 1, 0, 0. Okay, so the vector V is 1, 0, 0. There are only zeros. And the matrix D and the matrix E are given by 1 over beta A, then you have only one, so it's bidiagonal matrix. So only the first line is special. Everything else is 1. And E is also bidiagonal. It's 1 over alpha A, and then 1, 1. Okay. So these are the matrices, and I have just to tell you what A is. A squared is equal to alpha plus beta minus 1 over alpha plus beta, over alpha beta, sorry. Okay, so I let you check that if I take these infinite matrices and with alpha, beta, and parameter A, like that, and you enter this, okay, in the case where gamma and delta are 0, you enter this, and then it solves this algebra. Okay. Okay, now let me just try to, so here okay, you can compute a number of things for this problem, but here I'm just interested in the current. So I really want to compute this normalization factor. Yes? Sorry? Because it's a TSEP, so the TSEP R is 1. R is 0, sorry, R is 0. Okay, so this is just an example. Okay. Now, okay, the thing, okay, what was said before is that in principle, the only thing you need to do if you want that is to care about the largest eigenvalue of the matrix D plus E. Okay, and let me just say what will be the answer and then explain why. And the answer is that the answer will be that D plus E to the L will have 3 possible behavior. 4 to the L, grow like, I am interested only in the exponential growth. 4 to the L, or 1 over alpha, 1 minus alpha to the L, or 1 over beta, 1 minus beta to the L. And this is when alpha is less than beta and alpha is less than 1/2. And this is when beta is less than alpha and beta is less than 1/2. Okay, and this is otherwise. Okay, so essentially, this is this idea that you look at you have a matrix here and you want to find the largest eigenvalue of this matrix. But let me just try to interpret it. So if I look at the only thing, if I am interested in the current, is I am interested just in this matrix here. So this matrix is just a three-diagonal matrix, 1 plus alpha, 1 plus beta, A, and then 2, 1, 1, 2, 1, and so on. Okay, and there is 1, 2, 1, and so on. Now, and then I want to take that to the power L, and then to multiply by the vector here, and there will be the vector on the left. There, 1, 0. Okay, so the way I can interpret it is the following. I can think of a matrix, when I make this product, I can think that each term, when I expand it, is a walk. It is a walk which starts at the origin here, which ends at the origin, and then it does the walk which maybe goes up, sometimes goes up several times, sometimes it goes down. I can think of the matrix element. When I do this product, I can think that each term, when I make the matrix expansion, corresponds to a path. When this path goes up, there is a 1. When it goes down, there is a 1. When it is horizontal, there is a 2. Okay, I have a walk like that, except that because of these things here, there is maybe when it touches just very close to the origin, it does something a little different. The weights are not exactly the same. Okay, so two things can happen. Maybe the walks, if I look at all the possible walks, the sum will be dominated by walks which do not come often. Maybe they come 2, 3, 4 times near the origin. And therefore, d plus e to the L will grow like 4 to the L because it will be far away. So if it moves far from the origin, it makes a step horizontal, up or down. So there are 4 possibilities if it is far away. The other possibility is that this thing, somehow it's a kind of attractive wall for the walk. This thing is strong enough that the walk likes, most of the walk which will dominate are walks which are very close, remain close, so which means that they have an extensive number of contacts. In these cases, you have these behaviors. Now, you might trust me or not. If you don't want to trust me, you just look at the eigenvectors of this and look at the largest eigenvector, and you will get this answer. But the main idea, which is important for what will follow, is that you can interpret this thing as a walk. These walks have these weights, except that when you are near the bottom, just because of these parameters which are slightly different. That's it. And you get this thing. Okay, do you have any question on that? Now, what do I get out of it? Yes, but okay, you can. Yes, but you see, when you look at the Schrödinger equation in one dimension or on a lattice, okay, you have an infinite number of lattices, so the matrix is somewhat infinite. Still, you can find eigenstates. So, Yes, and if you, okay, in terms of really elementary quantum mechanics, what happens here would correspond to the appearance of bound states. Somehow, when I say I have this, you see, you can think of this path as a Feynman sum over all paths in quantum mechanics, and when these parameters are like that, it makes this would play a little bit like the potential of a Schrödinger equation, and it makes the weight here strong enough so that you have a bound state. So this is very much like finding a bound state of in quantum mechanics. It's not more or not less than that. You have other question? Okay. So let me come to the phase diagram. Now it's very easy because I have the current here, and I know, so for large L, I get 3 phases. I get alpha, beta, and then I get something like that. Here, the current is, for large system, is 1/4 because it's the ratio of this for L minus 1 divided by L. Here, okay, let me see whether I wrote it. Here, the current is equal to beta 1 minus beta, and this is the current which is given by alpha 1 minus alpha. So you have a phase diagram, and here is the first order transition. And okay, physically, or if you want some intuition, okay, you have this one-dimensional system. Now, the current through the system depends on, you see, you cannot flow too much through a one-dimensional system. So this is what's called the maximal current phase. And you cannot, for all these exclusion processes, you cannot, in the steady state, have a current larger than 1/4. Now, here, beta is rather small. So essentially, it's difficult to escape here. So beta is very small. So it becomes very, very crowded inside. And it's only beta which controls the density inside. Yes. And the reverse here is alpha is very small, so you have a rather low density, and it's the entrance rate which dominates. Okay, so this is the thing. You can compute many other things. Yes.
So if you were to, for example, try to do this numerically, what quantity would be used to separate the different phases?
So,
Cambiare questi poi sono delle latte in cieco. Quanto tempo ci vuole? Un minuto, un'ora, no? Prego, prego.
I continue. Okay, sorry. What?
So what quantity would you use to distinguish these phases? For example, if you wanted to, if you were to try and do this numerically, would you just use the current and that would be your measure of?
Okay, it turns out that the density will be different. Here, the density, the steady state density would be 1/2. Here, it will be beta, and here it will be alpha. So you measure the density inside the system, and yes, but correlations and everything. And this is the first order transition. You see, when you okay, when I say no, sorry, here I'm sorry. Here the density would be 1 minus beta. So when you cross here, there is a first order. The density jumps. Okay. Okay, this was just trying to illustrate. You can compute many things. There is a calculation, if people are interested in an exercise, you see the current is the true current in the steady state is given by this quantity. And as I said, this is a complicated thing. But imagine that I want to make a mean field theory. So I say, okay, I replace it by tau I, 1 minus tau I plus 1. So I forget that these two things are correlated. Can I compute the phase diagram? And the answer is yes. So it's a mean field theory. The phase diagram will be the same. But there are some about correlations that will be different. One major thing is that when you are on this first order transition, then the mean field will predict that there is a wall between two densities when you are at the first order, which is in the middle. And the true calculation tells you that this wall is delocalized. Okay, so these are small differences, but at least it's nice to have a mean field theory. Now, the last, unless you have questions,
Just also related question. So on the level of ground state, you think about like the gap and the gapless space in terms of the Hamiltonian when we look at the spectrum.
yes.
You know, this is actually like a steady state of a Markov matrix. So this condition also can be translated on the level of some gap closure of the matrix.
Yes. Okay, these matrices. Okay, you see, these matrix are not the one of the Markov dynamics. It's a different story. But you see, okay. Really, what the problem is what I have drawn before. Okay, which is still here. Okay, when you make this product, you can identify each term in the product as a path like this. You see, because along the diagonal, it means that you remain at the same height. When you have one off diagonal, which is one or above or alone, it means that you go up or down. Okay, so there is a one-to-one map between this and these paths. And except, okay, that's it, but when the matrix elements near the origin, they have this A and this beta there. So somehow it modifies the weights when you are just near the bottom. And the point is whether this walk, because you modify its weight, it likes to go away, or it is trapped close to the origin. Is it clear what I said?
Yeah, but I was more asking about like not the steady state, but approaching the steady state. We have
Okay, so this matrix method does not tell you something about approaching the steady state.
but these conditions translated on this kind of gap and gapless in terms of the equilibrium within the same.
Yes, yes,
So it's what also kind of gap.
yes. But I am not discussing that. Okay, so the TASEP is described by KPZ, in fact. So this has to do with the steady state of the KPZ equation and all that. But okay, okay. Now the last, I have 5 minutes, or I see. So it's very little. Okay. Okay. So let me just say, but unfortunately, I am not going to be able to do the full calculation. But okay. What I wanted to get is the large deviation. I am going to say it with words. Okay, the large deviation of the SEP. Okay, so I have to tell you what the matrices are. Okay, you can make many choices, but I wanted to use one particular shape of matrices. Let me see where they are. And okay, so this is the first thing you can try is to see, okay, you want to solve dE minus ED equal D plus E. So it's because now it's a SEP. And with the vector W equals 1, 0, 0, V equals 0, 1, V is 1, 0, 0. And the matrices will be of the following form. Okay, so you want to solve this algebra thing. Okay, it turns out that if you write this matrix is A times 1, 1, 1, 1, this will be a matrix, a diagonal matrix, A, and E is just the transpose, and A is the matrix which is diagonal, square root 2, square root 3, and so on, square root 4, and so on. Okay. And now I am interested in representing all this by paths. Now, when I want to compute the normalization, unfortunately, okay, time is running, so if anybody is interested, I can discuss it more precisely. But how can I represent E? So the first thing is that you just take thing, you put it into the equations, and you verify that it satisfies the algebra. But as before, I can interpret all these things by walks. Okay, so with a weight 2 here, 1, 1, 2. But now, you see, because of this matrix A, all the walks have not the same weight. They have a weight which depends how far they are. So, in fact, the weight will be this height here. So essentially, this is when I do the algebra, but when I look at very large system, I have a walk like that, but I am interested in a walk which are in a potential which depends on their height here. And this potential is logarithmic in y. And so the theory about finding the large deviation function is to think of walks which have a weight, the weight coming from this matrix A, and trying to see what is the optimal path given this weight. Now, when I have this path here, I wanted to do the computation, but I have no time. When I have a 1, it means that it's occupied. When I have a 1 down, it's empty. And when I have a 2, it might be either occupied or empty. And this allows to get the large deviation function of the density. Okay, so if anybody is interested, can come to my office this afternoon and I can explain it in more details. And thank you for your attention. In a higher dimension, I don't think you have. Sorry? Sorry? If you do what? Sorry, what? I think people have looked at trees. I think I have nothing in mind that I can answer, but okay, there are a number of problems in higher dimensions. There are things which can be generalized and other things which cannot. To my own knowledge, the steady state is not understood except for the average profile. But already the correlations are more difficult to get. And